Okay, once again, good morning to everyone. Father Dayan, I hope that you're still...
Yes, I am.
Maybe I locked you out and you have to go back in again. Oh, do I need to send a new invite? Let me know if you can see me.
Yes, I see you.
Yes?
I see you,
okay.
Father.
All right, good. So the same invite. You see, I send a link like this in case you're ever away on a Saturday. I send a link, and if I start a new recording, that same link is still, as long as the whole session is still open. All right?
Perfect.
So Michaela is away today, couldn't make it. And then that makes the 9 and the 10 of us. Begin always with a little prayer in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you for your many blessings, for the gift of life, and for having us here once again, safe and sound. Lord, we continue to pray for the people of Puerto Rico, the Caribbean, Mexico, and other parts of the world where there is suffering and strife due to natural disasters or human-made disasters, which make it even worse because of our stubbornness and our not being attentive to your divine will in our lives. Bless our session today. Bless all your children, especially those who are most in need of your divine mercy. And we ask this in the name of Christ our Lord.
Amen.
Okay. Any questions or comments from previous lectures or homework? No? Okay. It's a work in progress, so little by little we're going to get into it. And if you have your handouts for lecture 2, you can bring that up. I'm going to work on that today. If someone needs an extra copy, I have some extra copies. Yes? An extra copy. See. I have extra copies of chapters 1 and 2, chapter 1 and 2. We'll go with that. Chapter 3, which is what we're covering today. Anyone have chapter 3?
At least the same thing as for last week.
Chapter summaries, yes. So you can use this as a sample.
Oh, okay.
You need chapter 2, okay, there's 2, 1, 2, okay, so you need 3. Let me see if I have an extra 3. I have my copy of 3, but I can just do this. I can just have notes at the beginning here. Okay.
Okay, I have that.
I should do it. Okay, so here's 3. Sorry for the scribble up there. An extra lecture 2, anyone? Other one is hot. Very good. We have lecture 2. It's an extra copy of lecture. Lecture 1, we're done. For your records. Yeah, okay. Good, so I left off talking a little bit about these worldviews. That is just my opinion and experience. It's just something that helps me. It's like a key of interpretation that helps me figure out or put into context the origins that we're going to be talking about. The 3 big origins are the origin of the universe, the origin of life, and the origin of human life. Why? Because we're doing a bioethics. In other words, we're trying to integrate nature and the supernatural, all right? Or we're trying to integrate science in general, the empirical sciences, including biology and chemistry and astronomy, and theology, philosophy, belief. We're looking at reason and belief, actually, which are different dimensions of our humanity. The one should not deny the other. We understand many things, right? And science, especially empirical sciences, look at the understanding of things, the explanation of how this plastic is made, what is the composition of the plastic and the liquid inside, but then there's also belief. I may choose to believe that this doesn't exist, but that's a fantasy. It actually physically exists, at least we can sense it with our senses, okay? But I can choose to believe in the supernatural or not. The belief in itself doesn't make it right or wrong, but it is a belief. And we have many beliefs, right? Some are conscious, some are unconscious. But at any rate, if we look at these dimensions, it's more by size and how they relate to our external senses. We're just briefly reviewing the 5 classical external senses. We can even rank them maybe by importance or by more or less percentage of information that we receive through the senses. The first one is going to be sight, right? Sight. It is said that we receive maybe about 95% of our information through our sight. And then the next one is going to be hearing. Hearing. We cannot see sometimes, but we can hear. We can hear people on the other side of the wall, right? Sometimes if they scream loud enough, we can see them. And then there are going to be 3 other senses. The touch, right? Feel, which covers our whole skin, integumentary system. And then taste and smell, which are associated. Nose and mouth, more localized. But you notice that the head itself has all 5 senses. All right? And then the rest of the body only has, we can say generally 1, which is touch, but also blind people can perceive sound wave or waves on the floor, so it can be kind of an extension of an ear, analogically speaking. Anyway, so these 3 worlds are according to our senses. The stuff that we can experience normally with our senses without any real technology available. Just as nature put us here on Earth, we can see many things from the smallest that still can be seen. If we can see the smallest thing that we can see, right, then it's not microscopic. By definition, it's macroscopic. But then there's a world beyond that, which I'm just calling microscopic because it's beyond our normal range of sight. Give you an example. When I was an undergrad at FIU in the early 70s, studying biology, I was working in one lab in neurophysiology, and we were measuring the action potential, right, on a neuron, on the axon of a neuron. There is a creature in the sea that is known as a, let me see if I can move this around a bit. Yeah. Okay. It's known as a sea slug. Anybody know a sea slug? All right. We have them here, they're around the world in different places. Well, it's a nudibranch, yeah, but I want to look at the big one. Yeah, well, it's giving me all the nudibranchs, which are beautiful. But what is it? Is it Aplysia? Aplysia? I think it's Aplysia, no? Oh, just in case. Aplysia, yes. Wow, it's been 50 years ago, I still remember. It's not too pretty, Okay. Sometimes it's called a sea hare, like a rabbit hare, H-E-R-E, because of the projections here, which are, I think they're eye spots, no? They detect a little bit of light and shadow, eye spots. But it's a mollusk without a shell. But one thing that it has, well, it has two very well-known characteristics. One is that it puts out this purple ink, violet ink, like many mollusks do. The squid, you ever had squid in its ink, right? Black squid, delicious, all right? And the other thing is that it has giant neurons inside. It has a long axon of a giant neuron, which is, I think could barely be seen by the naked eye, but I used to make little probes of glass, which serve as an electrode. And a probe of glass is that you take a glass tube that is hollow, all right? Thin glass tube that is hollow, and you heat it up with a Bunsen burner, right? You heat it up, and when it becomes red hot, you can see the glass actually turn red, glow with the heat, then you pull it fast, and it will break. But it will break in a particular way that the two tips that break, they don't seal. The hole remains there. But that very tip is microscopic. And so once I made these little glass rods, which we use as electrodes, in other words, I would put now a salt substance inside, and then a little piece of wire, live wire, that I could hook to a monitor or a computer, and then insert that electrode into the axon of the sea hare, the aprecia, just the axon itself, all right? And what was interesting is that when I made those little glass capillaries, I could follow the glass with my eye toward the tip, right? And at some point, I couldn't see anymore, but I could touch beyond what I could see. I could touch the invisible because I could touch the tip, which was invisible to my eye, but I could still touch it. All right, so it's like touching something invisible. Just a little detail about the senses. Each sense has its own range. Anyway, back here to this three worlds. The other one, what we can normally see, depending with which sense, is a pretty large range. And I was talking about the stars, supposed stars in quotations that we see at night, little dots. Many of them are actually galaxies, which are millions of stars, but they're so fantastically far away that they look as a single dot. That would still be in the general macroscopic. But then the super macroscopic, that we cannot really see with our naked eyes, that we need some instrumentation, precisely when we telescope those dots, we can actually see the actual galaxies, right? Okay, so that would be in the super macroscopic. So for the microscopic and the super macroscopic, we need some kind of instrumentation. But again, we have to realize, and that instrumentation has become very sophisticated, right? From Leeuwenhoek's first microscope, which didn't look like a microscope at all. It was just a pinhead, the tip of a pin, and a lens over here where he could move the pin up and down and focus that little lens, right? To eventually electron microscope and proton microscopes where we can see atoms. It's been a big leap in 200 years, but we still have not invented all of the possible instruments that we could, right? So there's still a lot, and that's a huge field of technology. Think of medical technology, for example, and probes that can do surgery now that is minimally invasive through arteries and veins. It can do surgery inside without having to cut the person open. All right, so all this to say that it will help, at least it helps me understand a little bit these origins. And of the three origins, the universe, life, and humans, the origin of the universe, which is the biggest, do you think? The universe, how many say universe? How many say life, just organic life on Earth? No? How about human? Not sure? The rest don't care. I tell that to students. Whoever doesn't have an opinion, okay, that's all right. Really, it depends from what perspective, right? It is said that it's attributed to Thomas Aquinas that he would say, the great systematizer of philosophy, of Catholic philosophy and theology in our tradition, back in the Middle Ages, the Upper Middle Ages, that he would say, never deny, seldom affirm, and always distinguish, always distinguish. In other words, in one sense, Professor, in what sense do you mean the biggest? Of course, explosion-wise, the biggest explosion by far has to be the origin of the universe, because there is no explosion bigger than that. Okay, but theologically and anthropologically, of course, the biggest origin is the origin of humans. Especially if we're going by that Judeo-Christian anthropology that we are God's image, and only we are God's image, and God, only God is God, right? And if we are God's image, we are the image of the only supreme being, then theologically and anthropologically, the origin of the human has to be the first. Why? In other words, the question of why would God create an image? He could have created a universe without having to create his image and still be happy and content watching what's going on in the universe. Excited about his creation as it unfolds through life. So there was no necessity of creating us. We don't want to fall into, again, whatever image of God you give me is going to fall short, and whatever image of God that I give you is also going to fall short, in the sense that God, by definition, is always going to transcend the unknown of the unknown. And yet, because we are his image, we can have some kind of glimpse. But what we don't want to end up for sure is making God in our image, because that's what's happened invariably in history. And so other people reject those gods that have been made in our image, either a vengeful God or a happy God, or or an imperfect God, or God. All those images of God that we create and we generate are insufficient, right? So let's look at the origin of the universe for a little bit. And this is a poster. It's actually an insert in National Geographic. You're familiar with National Geographic, right? And this insert was, 2014, which was devoted to the origin of the universe, what they're calling cosmic questions. So this, which in common language is called the Big Bang, Big Bang. By the way, remember who is the one who proposed this theory of the Big Bang? I said? Okay. Sorry?
The Big Bang.
Yes, he was the Dutch priest.
Albert Einstein's friend.
He was a friend of Einstein. I didn't know that. Lemaitre.
Yeah.
Lemaitre. Sure, Lemaitre.
You can find pictures of them together.
Oh yes. Oh neat. Okay. Yes. So Lemaitre was a physicist. Oh, there you go.
Einstein quotes something about him, like that it was the greatest, like, theories for.
Yes.
Yeah.
Very good. Interesting. Okay.
Wow.
So Georges Lemaitre was, he was Belgian, right? He was Belgian?
Yeah.
And because the Belgians don't like to be confused with the French, it's very important, or vice versa. Like Poiret, remember Poirot? He's the character in Agatha Christie's novels, the detective. He's, because of his accent, he gets being confused by French. Anyways, dating me from last century Agatha Christie novels. Lemaitre is the one, he was a physicist, astrophysicist, and also a priest, a Jesuit. And he proposed this theory. There's a little saying attributed to him. There are two ways of knowing about the existence of the universe and the existence of everything that is. And he said, I have chosen both, meaning there's a scientific way of explaining the universe, but also there's a theological or religious way of explaining the universe, right? Mm-hmm. So I didn't know they knew each other. Thanks. He's the one who proposes this theory, what is normally known as the Big Bang. More scientifically, typically is referred as the moment of singularity. If you remember from math, from arithmetic, or from math definitions, the dimensions, right? Simplistically, the Cartesian simplistic model, what dimension are we in right now? 1, 2, or 3? 3-dimensional, right? Because there's height, depth, and width, 3-dimensional, right? It's volume. We all have volume, and we're inside a bigger volume, which is this room, which is in a bigger volume, which is the building, bigger volume, which is a university, bigger volume, which is Miami, et cetera, et cetera. So we are in a 3-dimension. Simplistically, I say, because what's the 4th dimension that is always with us? We cannot be out of it, not in this life. Some time has passed since I made that previous statement, right? And so the 4th dimension is time. Think about that. If time has passed, it means that the Earth has rotated a little bit since we started the class, for example, which we have all been in the same room since we started the class. So with regards to the position of our classroom on the surface of the Earth, in the planetary system, at least in the translation, you know, rotation of the Earth, and then there's translation of the Earth around the sun, right? In rotation, we have moved around, but in translation, we have also moved a little bit. So we may still be in the same place of this classroom, but we're no longer in the same time that we were when we started. So really, we're no longer in the same place either with the framework of the universe, even with the framework of our own solar system. We're no longer in the same place. Locally, we are, but not at the level of the planetary system. Okay, so the 4th dimension that is always with us necessarily is the time dimension. In fact, Einstein talks about the space-time continuum, space-time continuum. They are necessarily inseparable. Right. Okay, so 3-dimensional, we agree. 2-dimensional will be what? The screen, right? Your computer screen, the top of the sheet, when we keep it flat, and the top of the desk, etc. That's 2-dimensional. What's 1-dimension? 1-dimension is a mathematical definition. It's a mathematical definition of a point. All right, now we illustrate a point by a dot on a page. That dot could be made out of ink or pencil, but that dot, if we look at it microscopically, is actually 3-dimensional, right? It's a volume. It's a microscopic volume of ink or graphite, graphene, whatever the pencil is made out of. But mathematically, a point is a 1-dimension. So really, from one perspective, we can say the only one that qualifies as a physical point is the origin of the universe. It started as a point. Now that point had such density. Let me go up here. Oh, I guess I have to use the little bars, okay? Imagine that point, single point, has such density that it contained the entire universe. All the matter and energy, again, let's keep it simple for now, just as matter and energy, was contained inside that one point. Had to be, because before the one point, right, that single point, what was there? If this is the origin of the universe, what was there before the point? The mathematical point of singularity. Nothing. What we call conceptually nothing. Or we can call it abstracted, conceptually nothing, right? But it's very hard to illustrate that. And for example, in this poster has what I call artistic license. You've heard of poetic license, right? When the poet, in order to make the match and the rhyme, may take some liberties with the text. Novelists also take some liberty with reality for poetic license. Artistic license distorts, it doesn't represent reality quite so, it represents some image or some symbol of reality. And why is this model already inadequate? First of all, it's two-dimensional, right? We're actually looking at it flat, but it's trying to represent three-dimension. But this three-dimension is kind of this cone, there's this funny-looking cone that expands out, right? But if this is the point of origin, do you need more contrast, or should we try?
Yeah, that's better.
Better.
Yeah.
For note taking, it may not be, but you still have enough light to see? Yeah, okay, so better? Right. All right, so concentrating on this point of singularity here as origin, we're going to be faithful to in the beginning, all right, to origin, in other words, right after nothing, this first something. Then your artistic license is, for example, in this. What does this represent over here? You know, this should be, what should this be? If this was truly picturing creation or the origin of the universe, what should this be? This should be dark, nothing, right? What are these waves over here? It seems like another creation going that way, or what? To counterbalance. But so I'm saying artistic license in the sense that whoever designed this or committee, whatever, was trying to balance this. One of the aspects of drawing or art is balance, proportion, and harmony, these things, so it doesn't look bad to the eye, right? But this is definitely artistic license. In other words, we're going to be looking all the time in this program at detail. A lot of attention to the detail. So, for example, this, I'm just saying it's, to me, it's distracting because it doesn't show the beginning. It shows that there's something else going on over here, which is unexplainable. But he's trying to represent it with this cone, which is first a cone of inflation and then a cone of expansion. So there's two big moments, if you will, two general moments. The moment of inflation from a point to 4 dimensions, which happen in nanoseconds and millionth of nanoseconds, and then an expansion, so inflation and the expansion goes in the opposite direction of time in billions and trillions of years. Well, so far billions. So from billionths of nanoseconds to billions of years is the transition from that singularity to where we are today. And that has been estimated to be 13.5 billion years. Okay. So also I said that this is represented flat, but it's trying to give us a 3-dimension thing. But we need to expand with our mind's eye this 3-dimensional orange, yellow, orange area here. Concentrate first on the expansion area. If you could, please, in your mind, try to wrap this orange, funny-looking cone or half circle around the point, expand it, take that semi-orange and expand it all the way around like that, so that the point is really at the center of what could be a sphere that is expanding and exploding, right? So we want the point to be at the center.
Could you give me an example of third dimension? Say,
Third dimension?
yeah.
Okay. What is the easiest one to grasp is 2-dimension. This is in Cartesian. Remember, the René Descartes is the one who puts X and Y. The graph is 2-dimensional, right? X and Y. Which is the horizontal axis, X or Y, by convention? Could have been either one, but it's X. We determine the horizontal axis X, which is also known as the independent variable, typically time, for instance. It's not dependent on anything but itself. And then the Y has to become the vertical axis is the Y axis, which is the function of dependent on X. All right, so that's 2-dimensional, right? You can see a graph on the paper.
Yeah.
How do we represent Z? A diagonal that comes out. A diagonal is represented like a diagonal because we're representing 3 dimensions. We're representing a cube, a volume on a flat surface. But that Z comes out diagonally like this and also goes into the paper in the opposite direction. So a cube, you can imagine this book, is this 2 dimensions or 3 dimensions? You can look. Well, it has 2 dimensions, right? It has a horizontal and a vertical. So there's a flat surface here, and there's a flat surface here that is the same size as this other surface. But aren't there other 4 surfaces here? There are 4 surfaces here, which are perpendicular to these other 2 surfaces, right? So there's a total of how many surfaces? 1, 2, 3, 4, 5, 6. There are 6 surfaces here, right?
Yeah.
And what's inside? About 100 pages, 200 and 300 pages. That makes a volume, right? So there's in between these 6 surfaces, there's volume, there's something, either space or something inside. So this is 3-dimensional, right? It's got a horizontal dimension, it's got a vertical dimension, and it's got a Z, it's got a depth, whichever way you want to put it. But it's got 3 dimensions. Okay, just the room. It's even easier to do it with the room. The horizontal axis would be along the wall here, okay, from here to there. The vertical axis is the height of the room, and the Z axis is what? The depth of the room. So this is 3-dimensional, right? But it's actually 4-dimensional, because the other one, the other component that is inseparable with space is time. In other words, time has elapsed since I started giving this explanation. And that time has moved us, has moved the whole Earth around. Well, the Earth has moved in that time. So with regards to the planetary system and the universe, we're no longer in the same place. That's why time and place are linked necessarily. They have to be. So we're going to talk about those 4 dimensions at least. Anyway, I was just trying to point out that this is as simplistic, as complex as it looks. It is a simplistic model. But also the other observation that in the first half of the diagram here, of the caricature, the first half is occurring in billions of seconds. Billions, okay, a fraction, 1/10⁹. And the second half of the graph, beyond this, what they call in the dark age, this one here, where you see nothing happening in the caricature to here, now we're in billions of years. Billions of years. So let's get a sense for how much is a billion. So I told you that a billion is so large that even the scientific community has not fully agreed on if it's 10 to the 9 or 10 to the 12. It depends if you use the American system or the European system. I'm just going to use Excel as a little example for an exercise to facilitate the 4 operations that I'm going to be using, or actually just a couple, 1 or 2 of them. What are the 4 arithmetic operations? I'm asking you to dig back into beyond high school, into elementary school, okay? Because we get students in here who aspire to get a bachelor's. And sometimes they don't know how to do the 4 arithmetic operations. Okay, and what are the 4 arithmetic operations? Addition, subtraction, multiplication, and division, which really multiplication is a serial addition, right? Division is really a fraction. A division can be expressed in a fraction. 1/2 is 1/2, which is also in decimals. How much is 1/2? 0.5, right? Which is a number. So really, division can be expressed as a single number, as either a decimal or a fraction. So it comes down really to addition and subtraction as the fundamental entities, to add or to subtract. And they can't handle it, all right? But they don't know it. They have a high school diploma. So these are the challenges. I want to do a little operation here. Here we're going to put, what are we going to put here? We're going to put, let's start with days. No, let's start with seconds. And then we're going to go to minutes. And then 2 hours. Into days. And then from days we can jump to years. Okay. What I want to do is just 1 million. Okay. I'll put another. Let's count and see how long it would take to count to 1 million. Now, 1 million in scientific notation is 1 times 10 to the 9 and the 10 to the 6, right? And where's that little wiggle? Oh, here it is. Okay, the little vertical caret here is known as a power symbol. So you're familiar with this notation? Some are, some not. Okay, this means that 1 raised to times 10, so it's 10 to the 6th power, right? That's a million. How long does it take to count to 1 million? Because we got it. Okay, so let's see how long it takes to count to 1 million. We can go 1, 2, 3, 4, 5, 6, right? But if we say 1, 2, 3, 4, we'll probably say a little faster than 4 seconds. What's the standard counting in seconds? For example, if you're playing touch football and you have to snap the ball, whatever that's called, you know, fly, how do you count 5 seconds, the 5-second thing. 1 Mississippi, 2 Mississippi, 3 Mississippi. I learned it as 101, 102, 103, because that slows down the tongue enough to be a second. All right, but what I'm trying to say is we can count, and then when you get into, so it's fast to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but then when you get into 99,999, takes much longer to say than a second, right? Mm-hmm. So let's balance it out to 101, 102 as a standard, just the standard for counting from 1 to a million. What I'm trying to say is, let's say that it takes 1 second to count one number, one digit. All right? And so, how long would it take to count 60 seconds? It would take, I'm sorry, how long would it take to count to 60? To count to 60, it would take 60 seconds. So we can say up to 60 and 60, in other words, 1 count per second. I want to see how long it takes. How long would it take if we count continuously from 1 to a million? How long does it take? Just how long does it take, right? We're saying that we're counting 1 digit per second. Mm-hmm. So it will be 60 seconds. We have to get to a million at some point, and then we stop counting. All right, so how many seconds in a minute? It will be a little function here. You'd use equal, then you pick up this cell, and then you do the multiplier, which is the asterisk on top of 8. And we're multiplying how many? How many seconds in a minute? 60, right? So we punch in 60 and then we hit enter. Okay? So we can count in 1 minute, we can count up to 3,600, right? Okay, let's do something else here for ease of view. We want to put commas, right? Okay, and we want to get rid of the decimals. Good? Follow me so far?
In 1 hour, we can count it 3,000.
Okay, so in 1 minute, we can count up to 3,600. We count every second, right? Follow me so far? If I've lost anyone, let me know, please. Remember, the only wrong question is the question that's not asked, okay? All right, so how many, in 1 hour, we could count up to how much if we count every second of the hour? We could count how many minutes in 1 hour. Again, equal. We could pick up this cell and we multiply it. How many minutes in an hour? Again, 60, right? So we go that much. All right, so in 1 hour, if we count continuously every second, we could count up to 216,000. We're almost at 250,000 already, right? So what's your intuition? How many hours would it take? If this is 1/4, to get to the full million, it would be 4 times this, right? 4 times, yeah. So in fact, if we continue to count, let's say for a full day, this one, and how many hours in a day? How many hours in a day? The 24, right? Okay, so we've gone beyond. We've gone to 5, we could count to 5 million in 1 day. We can count to 5 million. But we're trying to get to 1 billion, actually. So we can say that 1 million could take more or less about between 4 and 5 hours. To count to 1 million. Now, 1 billion is, we're going to use the American million, a billion, which is what? 1 times 10 to the 9, right? 9 zeros. And I said that in Europe, this is considered 1,000 billion because their billion is a million million. So for the Europeans, a billion would be 10 to the 12, right? It would be a million million. In other words, 6 plus 6, the exponents add. Okay, so let's see how long it takes to count to a billion. Just to get this shape of size here, we can count to 5 million, but we need to get to 1,000 million, right? 1,000 million. So we need 1,000 times this. Okay, so let's see. We want to see how long would it take. We said it took about 4 to 5 hours to count to 1 million, right? Okay, how long would it take to count to 1 billion? We need 1,000 times. So how many days in a year? We'll use the standard 365. Yes, so follow me. All right. So 3, 6, 9. All right, that would get us almost twice. So it may be about half a year, approximately, a little over half a year, right? Because this almost got us to 2 billion, 1 year. So 360 into 2 is 180. So 190, about 190 days, let's say. Anywhere between 180 to 200 days, counting continuously 24 hours, 24/7, as they say, every second, 1, 2, 3, 4, 5, 6, okay? All of today, all of tomorrow, all of this month, all of next month, for 190 days for half a year, continuously to get to 1 billion. So just to give you a size, a proportion of how big these numbers are, because it's easy to say 10 to the 9. And then the converse of that is to say 1 over a billion in size or in time, all right? Which goes astronomically small. That's why I say that proportionally, the empty space between atoms is proportional to the empty space between galaxies. And remember, the empty space between galaxies allows 2 galaxies to go through and come out intact. All right? So proportionally, there is that much, and so we're mostly empty space. We're mostly empty space, really. But it depends on what world. We're talking about the microscopic world, or super microscopic, or just the normal stuff that we see around. So back to this little diagram for a moment. This point, which is that explosion and then the immediate expansion. I wanted to read a little bit here, just at the beginning. Almost 14 billion, between 13.5 to 14 billion. How do they estimate that? It's something called the background noise, or the background radiation that has been detected with telescopes that are in orbit, that are outside of the atmosphere, so they don't have the atmospheric interference, okay? And mostly the Hubble, but these telescopes have been able to detect what is known as background radiation, background meaning that they think that they are approaching the limit of the current universe, and then they can extrapolate from that somehow with some kind of sophisticated math to going backwards, regressing to when that explosion should have happened for that background to have the size and the characteristics that it has, that background radiation. That's how they come up with this date. It doesn't concern us because we're not astrophysicists. But the fact that they can put an approximate date to it. And then the first half, all right, more or less the first half of this big cone of expansion is what is known as the expansion, precisely. which is at the super microscopic. Look at the scale. The standard here is a millisecond. Millisecond is 1/1000th of a second, right? You got a second, 101. Then you got a tenth of a second. We can't even count it, that tenth of a second. Go to 100th of a second, go to a million, 1,000th of a second. Now go to 10 to the minus 32 millionths of a second. It crunches the mind, way too small. And all this happened, this expansion happened in that time, okay? So astronomically fast. In that time, the first, what we consider the today fundamental elements, which are these quarks. Quarks make up protons and neutrons. In other words, the standard model still holds, right? The basic unit of matter is the atom. We're talking about stable matter. We're talking about matter that stays as a page for more or less a period of time without disintegrating in my hand, all right? So stable matter, what is the basic unit of the stable matter? Let's take it by steps. Where does most paper come from? Most of it is shred, trees or cellulose, right? Shredded trees, shredded vegetable matter, which at the molecular level is cellulose. It's a polymer, it's a long molecule, it's a carbohydrate. Cellulose, we go deeper, but that's a molecule. Molecules are made up of atoms. So the stable basic unit of this paper is the atoms that are making up the cellulose, mostly, right? Okay, but it turns out that the atoms are made up of subatomic particles, which by themselves are not stable. They have to coalesce into atoms, and that's why the stable unit of matter is still the atom. But what are those? The three standard subatomic particles: protons, neutrons, and electrons. And the protons and the neutrons form what we know as the nucleus, and then the electron orbits around, right? Okay. There are other subatomic particles that have been discovered, but let's stay with the three classic ones. It turns out that at least for the proton and the neutron, they are made up of subatomic particles. For the proton, because they have mass, proton and neutron. And scientists, through huge machinery called colliders, hadron colliders, have managed to separate protons and get fragments. So if you get fragments from something, that means that those fragments are smaller and are more basic units. And those basic units are called what? Quarks. And quarks is a kind of a general terminology for a group of these subatomic particles, right? They have strange names like top, down, and spin and all that, and flavor. All right, but quarks make up protons and neutrons. I think that protons have 3 quarks and neutrons have 4 quarks. So when a neutron loses a quark, it degenerates, it decays into a proton, which gives it a charge, etc. But my point is that in that first 32th of a millisecond, the quarks came to be, were generated. I don't like the word created in science. If this is giving a scientific explanation, there is the word creation in here somewhere, which I'm going to take an exception to. I'll get to it. All right, but the quarks are generated from this explosion of, we can think of energy originally. There's some condensation going on. And then these quarks start coalescing into protons and neutrons. And eventually electrons start orbiting around those protons and neutrons, stabilizing into the first atoms. The simplest atoms are 1 proton, 1 electron, or 1 proton and 2 electrons. So you're going to get hydrogen and helium. The first 2 elements, the simplest elements, okay? All that happened within 0.1 of a millisecond, up to 200 seconds. 200 seconds by our count would take us about how long to count? 60 fits into 200, how much, more or less? 6 into 20, quickly, 3 point something, right? About 3 times. So it's about 200 seconds is about how many minutes? About 3 minutes, right? 60, 60, 60, and then you got 20 left over. So it's between 3 and 4 minutes. In the first 4 minutes, by the first 4 minutes of this explanation, because a minute we can understand a minute. You know, we can sit here for 60 seconds, we can understand a minute. Within the first 4 minutes of creation, the elements were formed. The simple elements of hydrogen and helium. All right? So you have the expansion first, and then you have now, then it's going, after that expansion, it's going to go into inflation, which is a different thing. Moving forward a little bit on the diagram. Elements start coalescing with each other, but you notice the jump here, all right, from seconds to years, to hundreds of thousands of years. Okay, so this is what is known as this beginning of this expansion, from the inflation to the expansion. So first we get the nuclei, which are made up of the subatomic particles, and subatomic particles from quarks. Quarks from this burst of everything. So everything had to be contained in that mathematical point of singularity. Because before everything, there was nothing. So everything in the universe had to be contained there. All right. Continued to expand. Now we're into the hundreds of thousands of years. What's going to happen is it becomes an incredibly slow process. So from an incredibly fast process that warps our mind in one way to an incredibly slow process that warps our mind in the opposite direction. Okay? So it seems like gravity is beginning to have some effect here by this coalescing or condensation as atoms begin to attract each other, forming molecules, and molecules continue to attract each other, forming macromolecules, and so on, until eventually we start getting condensations into galaxies, and from galaxies, planetary systems, all right? There's 13 billion years that I've been talking about. Here are the planetary systems. Let's see. So this is the 13 billion here. Backwards. We're here, and it's anyone's guess what's going to be later. But at this point here, scientists have discovered that there is this expansion going on. In other words, that not only it would be expected if this was a bang explosion of some sort, that the fragments, basically the galaxies and the suns that make up those galaxies, are expanding, are moving away from each other, and they would move also from the center. You would expect that center to become dark, right, as everything else is moving away from it, the original point of singularity. Not only is the universe is expanding, is moving away, let's say galaxies, take ours, the Milky Way is moving away from that point of origin. That makes sense because time has passed. But not only is it moving away from the origin, it turns out that the galaxies are also moving away from each other, but they're moving away from each other faster and faster and faster. So it's not just a velocity, not just a speed, like 55 miles an hour constant. You put the what do you call that? The autopilot, what is that called? The auto cruise control. 55 or 75, whatever you want to do. But you said it, and that's speed, that's velocity, constant, right? What's acceleration? When I go increasing, 55, 60, 65, 70, 75, 95, okay? Or decreasing, letting go or hitting the brakes. So the universe, so these galaxies are expanding, are distancing from each other in an accelerated fashion, which is counterintuitive. Because you would think that the away from the center would be a decrease, it would be a deceleration. All right, it's counterintuitive, but it's the reality, it's the fact, it's a scientific fact. There's no real explanation for it. What happens is there are models, okay? And one of the models is that it will continue to expand to the infinite. We don't know, but it's total guess, okay? And there are other two alternative models. One is that that eventually that acceleration will stop and it will start decelerating. And with the deceleration, then you're talking about an eventual collapse or a crunch. Or that acceleration cannot be sustained forever and something in the system gives that would rip it, that tear it apart, will shred it, as they say, and matter will eventually just disappear or collapse, but in fractions, in segments, in pieces, instead of collapsing into a single, let's say, secondary point from the original. But they're guesses, really. They're guesses, and it also points to the limit of our thinking in these senses, right? Because we're thinking kind of logically, and who's to say that the universe follows logic? All right, more to our point is back to this origin. Oh, and here too, this one is very important actually. Because so far I've been talking about matter and energy, right? But it turns out that this is what we call light in the sense of visible, detectable matter and energy. That detectable matter and energy is comprised here in this 4.5% of the entire universe. Detectable matter and energy, of course, our planet is matter, right? And the solar system where we reside is matter, and the Milky Way is matter, and all the other galaxies in the universe are matter. But they're also energy. For example, the sun is a star, and physically, the sun is made up of what? Mostly gas. Which one? Mostly hydrogen and helium. That, you know, hydrogen is highly flammable, right? Remember the Hindenburg, that Zeppelin that blew up, all right? So essentially the sun is a flaming hydrogen gas fire, okay? And it's giving off light and heat. Those are not matter, but energy, but there's a conversion, there's an equivalency. Einstein gave us that. What is the equivalency? E equals mc square, right? Where E is what? Energy. M is matter or mass. C is the speed of light, 300,000 kilometers per second. Squared. So the speed of light squared. But the important thing about this equation is the equal sign that has energy on as one term and has matter its equivalent term. So mass and energy are convertible back and forth. We can say in a sense they're two forms of the same thing, or two varieties, or two representations, two states of the same thing. Very powerful equivalency here. But it turns out that that is only applicable, at least for now that we know of, to the visible, to the detectable matter and energy, which comprises the galaxies. Planets and stars make up galaxies. Galaxies make up the universe, the matter, the material, but also they give off energy, plus the gas that is around, a lot of gas that is in these in the system. Very small, less than 5%. The other 75% is known as dark, but dark figuratively because we don't have direct access to it yet. We haven't invented an instrument that can detect it and can measure it clearly. But so we cannot measure it, how do we know that it's there, that it exists? Again, the background, and one that has been a great insight are what? They're appearing all over the place now. They were popular a few decades ago, the black holes, right? The black hole is a humongous suction that is sucking, has such density at the center. Here, locally, at the black holes, gravity wins. Gravity is so dense, pulling so hard, that not even light escapes. The light under the aspect of a particle, of a photon, right? Which is going to be sensitive to gravity. So that's why they're dark, because we see a blank. It's like looking at a mirror, and some place in the mirror, there's a blank. Let's say that the maker of the mirror forgot to put the mercury oxide, whatever it is that they make the mirror with, right? There's a spot that there was a dust particle or a fly or something on that part of the mirror or the glass that did not get the reflection. So there's a blank there. You cannot see, I cannot see my image on part of the mirror because it's blank, right? But the rest of it is around, and when galaxies move behind it, across, they disappear and then they reappear. So it's telling me that there's something there that I cannot see. Those are the black holes. And they're discovering black holes of all kinds of sizes throughout the universe. So that's getting at the dark matter. Something has to be mathematically at the center of that black hole to be sucking that in of such intense density that even sucks in galaxies, and they become part of that soup. They contribute to the density. Black holes tend to grow by themselves in that they're sucking, the more they suck in, the more dense they become. But that only accounts for a quarter of the universe, which is a substantial part of the universe. It turns out that almost 3/4 of the universe is not matter at all, is energy. Again, because to account for that background radiation that is appearing behind the galaxies, to account for that background radiation, there has to be, and accounting for all the matter that is included in the estimated black holes that there are, there's still 3/4, almost 3/4 of the universe is still unexplainable. And so the scientists are calling it dark energy. That's assuming that there's only matter and energy around. Right? Because again, it's testing the limits of our logic here, of our reasoning. So far, it's an interesting picture. It's exciting, it's bewildering, and there's a lot of math involved in this. But it's way, way far beyond my understanding. But of all this, to us, the most important aspect is back to that mathematical point of singularity. If that is the origin, then before that, there was nothing, but how did that come about? A creation presupposes a creator. But again, we're still within the framework of our own logic. Okay. So there's a supposition that something or someone had the power to do this and to establish the laws by which all of this universe is abiding. Okay? Scientifically, it has boiled down, if you will, to 4 fundamental forces, which I'll just mention now, but we'll pick up on them in the summertime in the course on environmental bioethics. And those 4 fundamental forces are the strong force, the weak force, strong force, weak force, electromagnetism, and the gravity. Again, strong force, weak force, electromagnetism, and gravity. The first 2, the strong force and the weak force, occur at the extremely small level. It has to do with the distance within an atom, the distance within protons and neutrons. And so these 2 are also known as, the first 2 are also known as interactions. Okay? Essentially, the strong force is what keeps the nucleus together, and the weak force is the decay rate of isotopes. Not to worry about it too much, just know that these first 2 occur in the microscopic world that I'm talking about, the super tiny small, whereas the other 2 occur at the large and the super large, particularly gravity that permeates through. And electromagnetism, it turns out that when electricity goes through a wire, for example, which essentially is a flow of electrons, it also creates a magnetic field. And gravity has also been described as a field. So the second 2 are also described as fields. So the first 2 forces are described as interactions, and the second 2 forces are also described as fields, right? But the fact that these are forces, what is really a force? Just like in the Star Wars thing, the force be with you. Well, in what context, Professor, are you talking about? What is a force? Really, a force is scientifically is a word that is used for lack of a better term. It's basically saying in a very veiled way that we don't know. We know that that's why interaction and fields are a little more descriptive. We know that there has to be some interaction occurring between protons. What is the charge of a proton? Positive. And so there's the table of elements, hydrogen, helium, see the little number on top, the red number 2. What does that mean? The atomic number, exactly. And it's the mass, right? And how many protons does a helium have? 2 protons, right? But they're positive. And what do we know about magnetism, electromagnetism? That positive and negative attract, but positive and positive repel. So how can 2 protons, which are both positive, stay together? They should be bouncing off each other, right? As far away as possible within the field of magnetism. That's the strong force. Whatever is keeping those protons together is only effective within the size, within the diameter of the nucleus, which is essentially 1 or 2 protons. If you go beyond the size of that 1 or 2 protons, the diameter of that little ball, that field is useless, has no force.
You mentioned that hydrogen doesn't have a neutron. Yeah.
Yeah, right.
That's
but then you get heavy
of course, that's too.
deuterium and tritium, right? When you get heavy,
hydrogen ion is a proton.
Right, yeah.
But
That's
then
so
with
cool.
the electrons, you get the deuterium and the donors.
Yeah.
I don't know about those.
And tritium, which is radioactive, and that was the water that the Germans were transporting by train, right? Oh, it's just water, yes, but it's heavy water, it's tritium.
One of my
We
students
were
was
working,
talking about this.
we were working on the
Yeah,
atomic
I told him,
bomb,
I
yeah,
don't know that it's
that was
heavy
high.
water.
Tritium. Yeah. The
So
third
it's
isotope.
radioactive.
Fast decay, yeah, it's unstable, all right? Okay, anyway, I'm getting kind of ahead of myself here because it's interesting and fascinating, but this is really, we'll get more into it in the environmental bioethics. So help us understand nature better. Just trying to point out that at that origin, a lot of stuff happens, okay? And we can ask the question, well, who, why? I mean, this is giving us a how, right? But who established those laws? Who established those laws? Or what established those laws? If you want to depersonalize the being with a capital B. For us Christians, we have an advantage because it turns out that that being with capital B is personal. In fact, it's three of them, which is a mystery of faith, all right? Okay, so much for the origin of the universe. We're going to go into the origin of life, but it's almost 11 o'clock. So I think we're going to take a little break here. And then I have 10 to 11. So why don't we come back at 11 and get into the origin of life. But before you actually leave, take a break. I'm going to be getting into this handle, which I didn't give it. Yeah, it should be on lock. It should be on lock. No, it's locked? Okay, let me check for a moment.
I used it before and it was.
Maybe there's
So back here.
Oh,
You will not wear it.
Oh, yes, go toward the entrance, yes, sorry. Okay, so, let's handle something. Yeah. We're gonna get into this origin of life, so if you wanna take a peek while we take a break.
Right, so hydrogen has no neutrons,
Right.
which is just regular.
Okay, officially break time, and let me see, Father Diane, I'm going to stop this recording so it doesn't get that heavy,
All right, Father.
and then
Mhm. But in various proportions, most of hydrogen is,
trying to get into,
And it's actually combined with another.
it's just
There,
a
here.
It has no.
okay,
it has no
so I'll start a new recording after the break in about 10 minutes, around 11, okay?
Perfect.
points.
Here we go.
Like